Hello, everyone. My name is George Rivera. I'm with tequipment.net. We're a Fluke distributor, and I have here with me John Burnett from Fluke. John, are you there?
Yep, I'm here. Hi, everyone.
Okay. We have a great webinar here for you. As you can see from the title on the screen, keep your machines running with fewer resources. If you have any trouble or have any questions, there's the chat screen. Please feel free to submit questions. I'll try to answer some as we go along while John's going through the webinar. And then as we proceed at the end, we'll have more of an opportunity to go into further questions. While we're waiting for a few folks to sign in, they might be running a little late. Let me just give you a little background on our company. We're a distributor as well as an e-commerce company. We call on a number of different markets and different types of product lines that we carry. As you can see here, it's not limited to this. You're welcome to look on our website for those categories. One of the nice things that we have on our website is just kind of a screenshot on the left side. There's left side filtering. Besides pricing and brands, you can filter by different categories, specifications. So if you're looking at multimeters, the range of the multimeter, or the type of logging. Can everyone just getting feedback? Or is everyone hearing me? Can I just get any comments on the chat window?
Well, I can hear you, George, but I don't know if any of the attendees can.
Yeah, I got your text that you don't hear. Yeah, I had hit the button for everyone to hear.
Yeah, that could have been my text. So.
Yeah, I think everyone should be fine. Let me wrap up this slide here. The internal portal that we have, that comment in there, is basically for convenience of the customer. You could log in and get your information, as well as there's an internal one for our use to answer questions very quickly for customers. And that kind of just gives you a little background on our company. And let me just introduce you, John, officially. John's a mechanical application and product specialist for Fluke with 30 years of experience in maintenance and operations. And he's worked with a number of industries in reliability programs, and he's certified Cat 2 vibration analyst, and with 20 years of experience in diagnosing machine faults, and is certified maintenance reliability professional, CMRP, and is a Navy serviceman with 12 years as an electrician with them. So, John, let me make you the presenter. All right, so we should be seeing your screen here when you're ready.
Okay, I think, do you see it now?
Yes.
Okay. All right, well, hi, everybody. Thanks, George, and I'm John Burnett, and I work for Fluke, and I understand the struggle that teams face day in and day out since I used to be a maintenance technician in the Navy, and I've worked for many, many years working with customers in all industries trying to improve maintenance. And over the years, I found that there's no quick fix or magic box, but we have learned from our customers what works and what doesn't work. So let's kind of talk about some of the things that that we've learned over the years. So first, let's talk about what's going on today. And maintenance teams in every industry are faced with a common problem: doing more with less, all with the cost of downtime increasing. So we're having you know, more and more struggles. And everybody, you're not alone. It's happened to everybody. And there's three main drivers to this problem: the workforce that's shifting, maintenance is getting more and more complex, and budgets are getting smaller and smaller. So we're having to do more and more with less and less. So if you look at the first one, which is the workforce, over the past few years, industrial teams have been a change in the workforce. Less people and less people dedicating their careers to the industry. One study done in the U.S. showed that you know, 200,000 workers have left the workforce, and a lot of seasoned professionals are leaving, and the younger workforce that's coming in doesn't have some of this the troubleshooting skills that have been around for many years, and this is causing a skills gap. The good news is a lot of the junior technicians that are coming into the workforce are more easily to adopt modern troubleshooting techniques and tools, and they have a broader range of assets. So we're seeing some changes in the workforce, and we need to be able to adapt to that. Also, maintenance and machines are becoming more complex and more automated. More of the motors are variable speed drives. Fans and pumps have controllers that auto stop and start, and our tech manuals are no longer technical, they're operating manuals. So we have to go to the internet to find this information. So our maintenance teams are becoming smaller and more cross-functional. Where we used to have maintenance tech, we used to have vibration analysts and electricians and thermographers. They're all different people. Well, now they're becoming more blended, and we're starting to see that the maintenance technicians now don't have the time for complex programs or high-resolution images. You know, you've got to keep a plant running. So how are we going to be able to do this? Awareness is becoming more and more enhanced. We're seeing that where we used to go to trade shows, we're now seeing our information on the web. We're seeing blogs and downloads and how-to videos. So the maintenance world is changing, and how we get our information is changing as well. Budgets are getting smaller and smaller. We're being asked to troubleshoot and fix more problems with less money. And we're seeing this from two different arenas. It's coming from two different reasons. One are economic downturns. We're seeing that not just in the U.S. but all over the world. And this is causing budgets are getting smaller and smaller, and we're finding out that if we don't use our budget one year, it's being denied for the next year. So we're seeing less and less funding, and we're seeing that this is causing a lot of struggles in a lot of plants. So what do we do? And so what I want to look at next is a comparison of things that we've been trying to adopt or change to over the years that on paper in an ideal world sounds really good, but then let's look at what reality, when it sets in, what that really means. So all of us are trying to get away from reactive maintenance. We're trying to get more to proactive maintenance, because we know if we can be more proactive, then we have more predictability. Our staff has time to schedule repairs and look for parts. We have a safer work environment with less machines that are catastrophically failing. We increase our maintenance intervals. Our machines last longer, more reliable. That means we have fewer failures, fewer downtimes, and we're able to anticipate our failures, and more peace of mind. So all of us know we would like to be more proactive. But then when we try to do it, that's when we run into a struggle. So let's look at some real world struggles. And I know that that most of you are seeing this. We all have tried to get away from reactive maintenance, because reactive maintenance means that we have these last-minute fixes. We have a stressful work environment. A lot of unplanned downtime means we have production losses. We have budgets that are being strained to the end. So many of us, and I know when I was in the Navy, I was a planned maintenance coordinator where we tried to plan our maintenance based on the calendar. And so we would have daily PMs and weekly PMs and annual PMs. And what we found out is we were fixing a lot of machines that we had just repaired the month previously. We were replacing bearings that didn't need to be replaced. And the real problem that we found out, and this was studies done back in the 60s by the U.S. Navy and the airline industry, and it's been confirmed every year since, is that failures of rotating machinery really can't be planned. It can't. The failures are 85% random. So even if we have a very good planned maintenance program, it's only 15% effective. So although it's better than nothing, it isn't perfect. So then many of us have heard and tried about trending, about predictive maintenance or condition-based maintenance. So we've learned that if we trend our machines and we know which machines are good or bad, then we can do our repairs, and it gets us away from the planned maintenance. But the problem is we don't have enough budget. We don't have enough resources. We don't have enough time. We're already busy 100% of the time with PMs and repairs. How do we possibly start trending? So this is some of the, in an ideal world, we would all have trending programs. We would all have proactive programs. But in the real world, it's just really hard to get these things going. So what do? Do we have to choose? And so a lot of the small and medium-sized companies feel they just don't have the resources to be proactive, and they go back to run-to-failure maintenance, or they go back to outsourcing just a few machines once a year to consultants, and they start using primitive techniques. So do we have to choose? And the answer is no. What we found out from some of our customers is there are some ways to see the benefits of proactive maintenance in today's environment of not having enough resources. And one thing that our customers have learned is things like start small and grow. You don't have enough time and you don't have enough resources to start a big program. You just start doing some proactive maintenance trending on a few machines and start getting some successes. So let's talk about some ideas. What are some ways that we can start small and grow and start getting some of the benefits that we've heard about when we just don't have enough time and resources? So the first thing, when we're trying to cover more with less, is let's first take a look at our machines, and let's classify our machines into 3 groups. And in this slide you can see at the top tier are just a few what we call production critical or star athletes. These are the machines that you really need a specialist for: your main turbine, your paper machine, your machining tools, things that really have a lot of not so much criticality, but they have a lot of variability. But below that, there's hundreds or even thousands of machines that are vital. But they're pretty standard machines in the middle tier. They're just motors, pumps, fans, compressors, and blowers. Very standard machines. In the bottom tier, the same types of machines, just less critical. So we can't just do just the top tier. We need to do a majority of the machines in our plant. Well, how do we do that? Well, one way we do that is we borrow some ideas from the medical industry. How does the medical industry handle millions of customers, millions of patients with only a few specialists? Well, the way they do it is they do it with general practice doctors and with nurses. So why don't we do the same thing with our machines? So why don't we screen out our problems with simple screening tools, looking for early signs and trying to find out if a machine is good or bad. If we do that, we find out that on average, about 80% of our machines are healthy. So why use a specialist? Why use expert tools? Why do a lot of analysis on machines that are healthy? So let's use simple tools to find out and screen out the 80% that are healthy, and let's not worry about them. On the 20% that have a problem, now let's bump that up to a diagnostic tool. A diagnostic tool is like your general practice doctor. Your general practice doctor is going to look for the most common problems. So a diagnostic tool for rotating machinery would do the same thing. And our most common problems are easy to fix. And for a rotating machine, the most common problems really boil down to 4: imbalance, misalignment, looseness, and bearings. That's about 90% of the problems with rotating machinery. And those are easy to repair. So again, let's screen out the machines that are good or bad, and then let's screen out the easy problems. Then the problems that are left, less than 10%, those are the ones that we need to elevate up to some specialists, our consultants, our in-house experts, and have them work on those. So just like in the medical industry, let's use our specialists for the machines the applications that we need a specialist, and yes, let's use our screening tools to find our common problems. So if we think about this, and because I do a lot of vibration analysis, I'm going to talk about maintenance tools from a vibration standpoint for rotating machinery. So 30 years ago, we had 2 tools. The high-end analyzer that took years and years of experience and somebody to analyze the squiggly lines. And then on the low end is a vibration pen, which just gives you a number. So on one end, you have too much data. On the other end, you don't have enough. What does 2.0 inches per second mean? Well, now we see there's 2 new categories. And these 2 new categories are the vibration tester, which provides a diagnostic report and tells you what's wrong with the machine, what to do to fix it. It gives us the answers we need, not just a bunch of high-resolution graphs. And the vibration meter that screens out and tells us whether it's good or bad. So if we think about it, this is the nurse and the doctor that the medical industry has. So instead of trying to attack all your problems with this with just a high-end specialist, let's use 3 different levels. The vibration meter to see if it's good or bad, the vibration tester to find the most common faults and tell us how bad it is and when to fix it, and then bump up the faults when needed to the vibration expert with the analyzer. Okay, now that we've kind of talked about that, let's talk about some simple tools that technicians can use. These aren't expert tools, these are technicians' tools that will allow you to be able to find out what's wrong with your machine, because like we said earlier, you don't have time for ground-up troubleshooting. You've got a plant, you've got to keep running, so you need to quickly find answers. So the first step is to screen out what's good or bad. And we would screen out problems using things like vibration meters, like infrared cameras and thermometers. So ways to be able to quickly find out, is it good or bad? And if you look down here at the bottom, you can see that on the screen to the right, you'll notice that we have orange. So that's a flag telling us that, hey, something is wrong with this machine. So once we screen out which machines are good or bad, then we call in the doctor. So the doctor for a machine is a vibration tester or a motor analyzer. These tools are going to tell us what the problem is, just like a general practice doctor, and tell us how to fix it. So if you read down there at the bottom, it says serious misalignment, and the recommendation is to align the machine. So now it's time to bring in some corrective tools. So in this case, we're going to use a laser shaft alignment. So we found out in step number 1 that the machine has a fault. Step number 2, we found out that fault is misalignment. Step number 3 is we need a tool that helps us with this misalignment. And today's laser shaft alignment tools will help us step by step. You see the as found condition on the left, the misalignment is, the alignment is in the red, and then over on the right, we can see that after it was aligned, now it's in the green. So a tool that helps us correct the problem. And then finally, a tool, we need to screen our machines one more time to make sure it's good. Before we return a machine to service, let's do a quick test and say, did we fix it? So you see the whole flow path from left to right, and this is all a matter of just an hour where we found out that a machine had a fault, we found out what that fault was and how bad it was, and a recommendation. We then went in and corrected that fault excuse me, with a laser shaft alignment tool. And then we did a quick second test, and we found out, hey, now that machine is healthy. So these are the kind of tools that technicians can use without having to be experts to be able to quickly find out what a fault is and to get it going, get the machine running again. Now, we've talked about vibration tools on rotating machinery. Well, there's more to keeping a machine running than just the vibration, just the rotating equipment. Because when you look at a machine, and I was an electrician for many years in the Navy, and I know that they would send the mechanics out first. The mechanics would say it's not mechanical, it's electrical. They'd call in the electricians. So think about it. To keep this pump running, we need to keep the motor running. To keep the motor running, we need to think about the motor windings to the left, then the drive, and then power input. So input power, the drives, the motor windings, the insulation, mechanical, that whole path, if anything goes wrong, this machine is going to go down. So that means that we need to use different tools. We need to use electrical tools, scopes, power quality, digital multimeters on the electrical portion of this troubleshooting. We need to use mechanical tools for the rotating machinery. And then our infrared imagers can be used to kind of help the electrical and the mechanical. And then finally, process tools to keep the flow going, to keep the pump pumping and that kind of stuff. So a lot of teams have, by mistake, picked one tool or one technology and then try to measure everything. A better way of doing that is matching the likely failure modes. And when you find out what you expect your failure modes to be, then you can match the right tool to that failure mode. So for example, if you look down here at the bottom, if we look at the vibration, we need to, for rotating machinery, we're going to be looking for imbalance, looseness, misalignment, and bearings. Where for electrical, we're going to be looking for harmonics, distortion, and doing load studies. For motor insulation, motor speed, torque, power, efficiency, insulation. And then for process tools, pressure, temperature, and milliamp. And then over on the left, thermal tools can be used to look for faulty connections, electrical, overheated bearings, mechanical, and tank levels process. So instead of just using one tool and trying to use it to find everything, which doesn't work, we need to use the right tool for the right failure mode. Because how can we be a machine psychic with just one tool? So if you look at it, here's a graph that we call the potential failure curve. Now this is a conceptual curve. It's not there really isn't any time based on this. This is more of a thought process, because when you think about it, when a rotating machine, now there's different curves for different assets, but this is one for rotating machinery. When a machine first starts to fail, it fails in kind of this degradation curve. When it finally fails over to the right, just before it fails, it's hot to the touch. Before that, it's audible. And then before that, we can see it with thermography, and then electrical, and then way before that, vibration, ultrasound, and oil analysis. Now, it used to be years ago that we would try to push our luck and try to get down as low in this failure curve as we could get before we repaired the machine, to try to get as much life out of the machine as possible. Well, we found out there was two problems with that. Number one is if we wait too late, the cost to repair is exponentially higher. Why? Because somewhere up here in the yellow is when a machine, when the damage is done. The bearings are already wasted. It's already too late, and even if we go in, so we have to fix these bearings before they get wiped out. Because if we wait until it's just before the audible noise, now we have to replace the whole motor where we could have replaced just the bearing. The other problem is energy waste. If we let it wait till it's too far down in the failure curve, the machine is starting to wear out and it's running bad, and our energy is exponentially higher. So what we've learned from this curve over the years is we want to find out up in the green when a machine first starts to have indications of problems. And by using vibration on rotating machinery, we're able to know when the bearing goes from slight to moderate to serious to extreme. So now we can plan the repair. Now we know when we need to schedule the repairs and when we need to fix this machine. Okay, now a question that we get asked quite often is, well, how come I keep fixing the same faults time and time and time again? When I was in the Navy, this happened to us all the time. It seemed like we were fixing the same bearings and the same seals over and over and over again. Why was this happening? Because we weren't fixing the root cause. The root cause is imbalance and misalignment. So if we ignore imbalance and misalignment, then what's going to happen is we're just going to keep replacing bearings again and again. When I was in the Navy as an electrician, we would replace the bearings on the motor, the mechanics replace the bearings in the pump, and then a year later, we're doing it all over again. Then we started finding out that it wasn't the bearings. We started aligning machines, and we started balancing machines. When we did that, bearings lasted for years and years. So that's what we recommend. So it's kind of a two-step process. The first step is we need to find out what our faults are. So by using a vibration tester, which is a quick and easy tool that a technician can learn how to use in just a few hours, now you know the answers you need to know. You know what all your faults are, because this tool is designed to look for the most common faults: misalignment, imbalance, looseness, and bearings. And don't ignore those and just replace the bearings, because if it's misalignment, we need to fix the misalignment, because even a moderate misalignment is going to cause your bearings to wear much rapidly. So now we need to think about using some of today's step-by-step laser alignment tools, because in the past, alignment was a long process. You needed an expert. You needed a millwright. You needed to have reverse dial indicators. It took hours and hours because you had to do the math again and again. Well, today's laser alignment tools can walk you through step by step, so that instead of, and you can do a laser alignment job in less than half an hour. So in 15, 30 minutes, I can align a machine instead of half a day or even a whole day. Well, now, instead of aligning just the few machines in the plant, I can align a majority of the machines in the plant. So if I can align my machines and get them running smoother, I save my energy waste that I've been causing problems with, and my bearings and seals will last their full life instead of being cut short. So think about root cause analysis. Okay, so we talked quite a bit about vibration, but let's kind of open this up a little bit, because we want to think about other types of tools, because we introduced electrical tools and vibration tools and also thermal tools. Well, there's different levels, and we need to have the right tools in the right hands. So think about the different tools. Over on the left are the on the right are the electrical tools, in the middle are the vibration tools, and on the left are the thermal tools. And also think about the tools in their levels of categories, in that there are screening tools that help us find out whether the machine is good or bad. There are diagnostic tools in the middle that help us determine what the fault is and what to do to fix it. And at the top are the expert tools, when you really have a complex problem and you need to have an expert. Okay, one thing that we want to kind of do as we kind of start wrapping this thing up is, what's really important is to get information, get answers, because a lot of important information is locked up in these high resolution images and complex plots. We just don't have time to have to go dig through all this information. So let's look at our reports to see if our reports are giving us the answers we need, because the technician that doesn't have a lot of time needs to get answers. You don't have time to go looking at all this data. So there's 3 different levels of reports. There's the enterprise report, which is kind of a high-level report that tells us kind of what's going on in our plant as a plant-wide kind of report. Then we have connected reports, and these reports are reports that bring data from different tools like Fluke Connect does, and brings multiple tool information together. And then finally, the individual tool report. So when you look at tools that you're going to be using for your maintenance technicians, look at, does it provide the answers you need? So the answers that we feel that you need to have to make it an effective tool is, you need to be able to know, number 1, was the tool set up correctly? Number 2, are your measurements good? Number 3, what is the answers? So does that give you the answer you need about the fault? And then finally, is there an action step? How to fix the fault? So if you look over the mechanical tools at Fluke, you'll see that the reports that we offer, now this is pretty small, I admit, so I'm just kind of explaining, giving you an overview right now, but if you get a chance, talk to your Fluke representative and they can show you these reports. But in these reports, they're going to cover all 4 of these. Each of these tools, you're going to be able to see, you're going to be able to validate that you've set the tool up correctly. You're going to be able to validate that your measurements were taken correctly. You're going to get a diagnosis that's going to tell you the answer of what the fault is, and then finally an action step on how to fix it. Not only in our mechanical tools, but also in our electrical motor analyzer and in our thermography infrared cameras, the same thing. This useful information of answers, not just a bunch of numbers. Because numbers don't tell you what you need to know what's wrong with the machine. Okay, and how do I get answers? And again, I'm going to use vibration as an example. So what I want to compare is the training and time investment compared between a screening tool and a diagnostic tool and a specialist, an expert tool. So if you look at this, the people and the tools, so from the top, an expert analyst with advanced analysis tools is required for a small percentage of the most critical complex machines. Most of the machines in the plant can be diagnosed using a maintenance technician with a tester, and then entry-level technicians can screen. Now, to put this into perspective, let's look at the training and time required. So an expert analyst using a vibration analyzer takes 2 to 3 weeks of training, 5 years of experience, and every time you go to analyze a set of data, I've been analyzing data for 25 years now, it takes 30 to 45 minutes on even a machine that's healthy. So there's a lot of labor, a lot of training, a lot of knowledge. Well, if you look at the diagnostic tool there in the middle, 8 hours of self-paced training, you already have the experience you need because you already know your machines, and it only takes 10 or 15 minutes to get an answer compared to 30 to 45 minutes for the specialist to get an answer. So this doesn't replace the analyst, so I don't want anybody to think that, hey, now we've got something that you can replace a vibration analyzer. No, but this is a tool that you can use on a majority of machines and find the most common problems so that your specialists can focus on the very critical complex machines. And then down at the bottom, the vibration screening tools only take about 30 minutes of self-paced training and you're able to screen machines. So what this is showing you is that it just isn't a very time-effective, labor-effective, or good use of our resources to use specialists, to use experts on standard rotating machinery. So let's use some screening tools to help out our experts, and let's use diagnostic tools. And if we use these 3 different tools on 3 different levels, we can cover all the machines in the plant, not just the top few machines in a plant. Okay, so I talked about screening tools. Let me real quickly show you an example of a vibration screening tool. So this is a vibration screening tool, and as you can see, you would press it into the bearing of the machine and take a quick measurement, and you'll see we've taken our first measurement, and when we first started collecting data from this machine, notice that it's green. And if we look at the chart, you can see that it's low vibration. And then months or even a couple of years later, you'll notice the vibration level has increased, and now it's into the yellow, or into the orange. So vibration screening tools are going to tell us whether a machine is good or satisfactory, which means no action is needed, or if it's unsatisfactory or unacceptable. So if it's unsatisfactory or unacceptable, the machine has a problem and now further testing is needed. So the purpose of the screening tool isn't to tell us what the fault is and what to do to fix it. It's simply in a few seconds telling us quickly, is the machine good or bad? So screen out 80% that are good, and now only 20% have to be bumped up to the next level. The next level is the diagnostic tool. For standard rotating machinery, and that's motors, pumps, fans, compressors, blowers, gearboxes, almost all of our rotating machinery is pretty standard. We can use a tester, and in 10-15 minutes we can know whether there's any faults and to know what those faults are. And again, there's really 4 faults that we're looking for: imbalance, misalignment, looseness, and bearings. So there are 2 different ways that we could analyze data. An expert could do manual analysis, which, like we showed you earlier, takes years of training, takes a lot of experience and knowledge, and it's very labor intensive. A vibration analyzer is going to go through 4 steps. A human is going to identify the peaks, is going to measure the amplitude of the peaks, and then look for patterns in the data. Well, there's an automated vibration. So we've been doing manual analysis for over 30 years. So vibration experts have been able to develop a program that has automated this process, the same steps that a human analyst would do. It doesn't replace the human analyst, but it takes first crack at it. Well, let's eliminate the common problems, and that's what computers are good at. Computers are good at crunching numbers. Let's let them do that. And the way they do that is they first find the largest peak in the data, then they use a baseline of hundreds and thousands of data that's been analyzed by humans over the years. Pattern recognition is set up, and so it's going to automatically give us a fault, and it's going to tell us whether the machine is good or bad, and it's going to tell us what the fault is and what to do to fix it. So again, let's screen out 90% of the common problems using a automated diagnostic tool. That way only 10% of our problems need to have somebody spend hours analyzing the data. The training for a vibration tester isn't months or weeks or even days, it's hours. You can learn how to a self-paced training program using DVD videos and using exercises, using a training book. You can teach yourself the basics of vibration analysis so that you can run a vibration tester and run a program. Again, you're not going to be a vibration expert, but you're going to be able to know enough to know how to find the common faults. Let me run over some quick ROIs just to give you some examples. There's been some return on investment studies done by the Electric Power Research that shows in all industries that plants that run in reactive mode are much more expensive than planned maintenance or condition-based maintenance. You can see that planned maintenance is 24% savings over reactive, and predictive or condition-based maintenance is 47% savings. Let's look at some other cost savings. There's a large company that implemented predictive maintenance program on hundreds of their rotating machinery over 25 years. Every 2 years they do a cost of benefit study, and they've been documenting their savings of over 20 to 1. And these savings are based on 6 different benefits that they track every 2 years, and they've proven that for every dollar they invest in proactive maintenance, they're saving $20. So these programs really do work. Even a small company was able to transition from reactive to preventive to predictive, and over a 10-year period, they were able to cut their maintenance budget in half on 600 critical pumps, and their machines were running twice as long before having to have repairs done. So everybody can see these savings. So the last thing I'm going to leave you with is, what does it take to start up a program? Now, number one, don't start too big. The number one killer of starting up a proactive maintenance program is trying to start too big. The secret to success is to start small and grow. Just start with 20 machines. Start trending those 20 machines. Use screening tools like vibration meters and thermal imagers to tell us whether the machines are good or bad. Then move up to diagnostic tools. Once you start getting some successes, then wave the flag, document your saves, tell everybody how much money you've saved. Then people are going to get, you're going to get buy-in, you're going to get budget, and you can grow the program. That's the best way to start a program up, is start small and grow. The number two killer of a program is trying to buy just one high-end tool and try to do everything with it. Like we showed you earlier, it's much better to use screening tools and to have multiple screening tools than one high-end tool, and that way you can match the right tool to the likely failure modes. Let's find out the electrical problems and mechanical problems, and let's find out what's going wrong with our plant. And then finally, the number 3 killer to a program is data overload. If you start getting data upon data upon data, a bunch of numbers, if you don't get answers from that data, it's not doing you any good. And it's like looking for a needle in the haystack. And you see the picture over on the right, by stacking more data, by stacking more hay, doesn't make finding that needle any easier. And the same with machines. We need to find answers, and just getting a bunch of numbers doesn't tell me what's wrong with my machine. Okay, so as we wrap this thing up, the last thing I want to kind of leave you with is Fluke can help you. Talk to your Fluke representative, and they can help you start or restart up a proactive maintenance program. Okay, so we talked about some tips for easily identifying machine faults. We talked about some simple steps for comprehensive maintenance and repair workflows. We talked about some best practices for combining multiple tools for a more complete picture. And we went over quickly how to use some of these tools to get answers with minimal training. So now I'm done talking, so let's open it up and see if we have any questions.
Hi everyone, it's George again. I just posted it on the chat. If there's any questions that you might have, just post them there. It's a little easier to do it by text. In the meantime, there was an couple earlier questions while we're waiting for any additional ones, John.
Okay.
So if you talked a lot about vibration, but you know, what if you had a limited budget, you know, is that what we need to get first, or do we get a thermal camera or some other tool? What tool do you want to start with?
That's a great question. So what I would recommend, instead of buying one high-end vibration analyzer or one high-end thermal camera or even one high-end electrical tester, it would be a lot better to get some of the low-end screening tools. So for example, if you had a vibration meter and one of the lower resolution thermal cameras, you could buy those two tools for less than the cost of one high-end vibration analyzer along with an electrical tester, and that way you could start your program. And not only that, those tools are much easier to use, which means a lot less training. So again, let's start by crawling before we walk, before we run. So let's start off by using some simple screening tools, and maybe using 2 or 3 simple screening tools, and start finding out which machines are good or bad. And then once we start our program and get things rolling, then we move up to start diagnosing and buy some diagnostic tools, and then we buy some correction tools. So kind of do it one step at a time.
You had a slide where you were talking about the importance of the equipment. So I think that how critical is that equipment if it fails to your process? I would think so. If you're trying to select between them, that would help too. You know, what kind
Absolutely.
of instrument? If you don't have to worry about pumps, then that eliminates. And you have more electrical issues, and then
that's
you focus
exactly
on those.
right. So think about your likely failure modes. What is causing you your biggest problems? Now, if your failure mode is bearings and motors that are, you know, blowing up, well, then maybe you want to think about, number one, if I've got a lot of motors blowing up, then I probably need to get some electrical testers. But if I've got a lot of bearings going, I need to, number one, screen out and find out which machines have bad bearings. But then number two, I might need to find out, is it really the bearings that are bad, or is it the imbalance or misalignment? But you're exactly right. Instead of just buying one tool, like, for example, a thermal camera and trying to just run your whole predictive maintenance program off of one tool, think about what are your failure modes in your plant. You know, I see a lot of bad bearings, or I see a lot of coupling problems, or I see a lot of electrical connections or a lot of overheating. That's going to help you figure out what tool you need. Yep, good call.
The other, at least kind of the next question, so as you're trying to figure out what's important, how do you find customers are organizing their data? You know, the ones that don't have some sort of enterprise maintenance reporting tools. Are they just putting in a Word document, or how are they organizing things? And
that's a good point. You don't, like everything else, don't start too big, don't start too complicated, don't start with the most complex thing. So I would recommend not starting with a high-end, you know, program that takes years and years to set up and get going. Like this picture, this screen is showing up in the upper right, that's an Excel spreadsheet. Just start with a simple Excel spreadsheet. And Excel is great because in Excel, you can start by, number one, getting a list of all your machines, and then build yourself some columns and start rating your machines, your critical machines, by number one, you know, is this machine affecting my production? Number two, is this machine affecting safety? Is this machine affecting environment? Is this machine, so the things that are important to you, that's going to be the way you rate these machines. And then when you get all done, way over on the right, you could add up all the ratings of all these different categories for your machines, and that's going to give you an idea. And this is a real good learning experience to kind of let you learn which machines are really critical. And you may find out that a machine that you thought wasn't that critical, you find out that if that machine goes, the most important machine in your plant goes, and that machine's a lot more critical than you thought. So since we all have limited resources and we're having to do more with less, the first exercise is let's find out which machines are critical, and then the second step from that is that would determine, number one, which machines you go after, but also, you know, how often do I want to screen this machine? How often do I want to diagnose this machine? So yeah, just start simple and just use Excel spreadsheets. Then that's kind of the way, because when you make this first Excel spreadsheet up, it's not the final version. This is a work in progress. This might take a few months, you know. So if you get it just 80% done at the beginning, and then over the months get it better and better, and then once you get this thing started, you get your program rolling, then think about going into a CMMS program, a computerized maintenance management program, or a bigger program. But let's start small and grow.
How do I get a budget approved for some of these tools? That was the
so
frequent, what I got a couple of those type of questions.
Good question. So part of this is you're going to need to make a case for the need. Now, Fluke and our representatives can help you with some ROI spreadsheets. Part of this is by using an ROI calculator. There aren't any, you know, you can use some estimates to kind of find out what is your downtime, and you know, and that's something that you're going to want to kind of look into, because let's face it, if you have one medium-sized motor pump go down and you figure out how much that cost, well, that probably paid for a vibration screening tool and a low-cost thermal imager. So that's what I would do. And again, start small. Don't try to say, I want to buy these 8 tools and I want to train up a vibration and a thermography and electrical team all at once. Again, start with, hey, what if I save just 1 or 2 machines in a 2-month period? Well, if I saved 1 or 2 machines, I could have bought a couple of screening tools, and that's how you get your program started.
Yeah, if I could add, I've started out as a production engineer and manager, a supervisor at a chemical plant, and how I got into instrumentation was we had a 100,000-gallon tank of acid run over because the level instruments weren't working correctly, and so I'm like, this is crazy. How can we not have working equipment? And got interested in having backup equipment. And I mean, it's unrelated to a motor pump problem, but
No, that's good.
there's environmental. It's not just ROI in terms of saving
Production.
money.
Yes.
Yeah, production, downtime, and so on. There's it could be an environmental or a safety incident that you could prevent by having working machinery.
Absolutely.
Yeah, so those are tough to quantify, but you could use those as part of your justification for funds.
That's right. So another thing to think about is a lot of times you had something that just happened, and that's a good justification. So if you think about it, man, we just had a machine go down, took down half the plant, and we lost, $50,000. Well, that's the perfect time to run out and say, hey, boss, if we would have had some of these simple screening tools, we might have been able to prevent that. Well, what if we didn't have something that just went down, last week? Well, then sit down and think about what has happened the last couple of years and write down, how you've lost money or how you've had a safety concern or you had an environmental impact. Write down some justification that's happened in the last couple of years and say, hey, look, boss, I'm thinking about, remember this happened 6 months ago and this happened 12 months ago and this happened 18 months ago. We need to look ahead and be ready for these things because they're going to happen again. That's the only thing that history has taught us is it's going to happen again. So those will help you justify a program.
I have one question which maybe you can understand. I asked the person to clarify it, but I haven't heard back yet. It says, what is the average time that changing or charging a maintenance program can take, and can it be estimated? I'm not sure.
Well,
maybe.
Yeah, it's a little hard to know because there really are so many variables. Again, if you were to get corporate, in an ideal world, we would get corporate buy-in, and from the very top, the CEO and everybody down would say, we're going to go from reactive maintenance to proactive maintenance, and we're going to use vibration thermography and electrical testing, and we're going to start this program up. And if you had something where it was like that, it's probably going to take 2 or 3 months just to set up the program, and then it's probably going to be 6 months or longer before you start seeing some results. Where if you started small and you do it under the radar of everybody around, and you just did a few machines, then it's not going to take months and months and months to get the program going. It's just going to take, a month or two to start seeing results. Now the thing is, once you start seeing results, then you can grow that program. So the answer is, it's not something that's going to happen overnight, whether you started big or you started small. But if you try to start big, then it's probably never going to get off the ground before it fails. If you start small, it's still going to take a couple of months to start seeing some results. It's probably going to take months or even a year before you start seeing some real substantial results, and you're going to have to keep the thing going. Now, what a lot of people have done, they've made the mistake of they get a program going in a year or 18 months, it's showing good results, and then everybody says, hey, this is going good, now we can stop the program, and then you go right back to where you were before. So it's something that you have to do. Once you get it going, you have to keep it going. You can't let it go back down again, because then you're going to be right in the same boat you were in before.
Well, John, we reached our time limit here.
Yep, we did.
Yep. If everyone's going to get an email copy of of the presentation. And if you have any questions, you can reply back to that email, or you can email me directly at jorge@teequipment.net, or use our main email for the sales team at teequipment.net, and we'll be happy to answer. We can arrange, depending on your application. I'm an engineer. There's a vibration, certified vibration analyst here, certified thermographers as well. Depending on what you need, we should be able to help you. And if not, we can arrange for someone to come out and visit with you.
Perfect.
Again, thank you, John, for a great presentation.
Thank you, George. Thanks, everyone.
All right. Goodbye, everyone.
All right. Take care.